Okay, it turns out that the convenient way to think about CFGs is in terms of parse trees. So a parse tree is essentially a way of representing the sequence of production that were used from the start variable to generate a word in the grammar, and it's best explained by just looking on a figure. So consider the following grammar, which is not a minimal grammar, but that's quite okay. S goes to A, SB, or go to BAS, or SS, or AB, or BA, or epsilon, right? So this is just a grammar that generates all strings that have a balanced number of A's and B's, right? It's not the minimal, by the way, but who cares? And now think about the sequence of the derivation that is shown in the bottom, right? We just generate from S the string ABB AAB, right? And the idea is that now we start with a tree, right? In the beginning, we have the variable S, and then we use the production, for example, S goes to ASB, so we create a leaf A, written it as A, we create a node S, and we create a leaf B, right? And we continue expanding in this way, right? Every time we use a derivation, we put the children or the production string that is derived from the variable, we put this as children of the current string, right? So what we get is this tree where every internal node is a variable, all the leaves are terminals, and the string computed is just the leaves of the tree from left to right. Right? So this is the production, and this gives you the parse tree of the language. Sorry, the parse tree of the word. And for a lot of application, we are interested in the parse tree because we are interested in the inherently we want to do the parsing because we want to know the logical structure over the string that we have, right? Just think about you have a numerical expression and you have a C program. You are interested in the logical structure, and this parse tree gives you the logical structure. So that's really the main motivation to use context-free grammars or languages. The problem, of course, is that things can be ambiguous. So a grammar is ambiguous if for the same string there's two different ways to generate the same string with two different parse trees. So here's an example. This is just a sequence of numbers where you subtract one from the other. This is this grammar, 1, 2, 3. And you look at the expression 3 minus 2 minus 1. The parenthesis here is added for understanding, not because it's part of the language. And this is the other one, right? Now, conceptually, we really care whether it's the left or the right, because when we compute it, we compute the left one and the right one in different way, right? So that matters, right? In particular, the standard way we do things, it's the right interpretation is the right one. And as you can see, you can get both interpretation using this grammar, right? Now, in this case, this is not too difficult. You can get over this problem by playing around with the grammar. So you introduce a new variable C, where C generates a terminal, and then you force S to go to either minus a terminal or to S itself, right? So you get a unique parse tree, which is good. And in fact, this is the right parse tree for as far as numerical operations. So that's good. But of course, there are situations where you cannot get around ambiguity, right? So there are grammars that are inherently ambiguous. One such grammar is the grammar where we have A to the n, B to the m, C to the k, where either n or m are equal or m to the equal to k. So first, this is clearly context-free grammar because it's a union of two languages, right? One of them is A-N, B to the N, C star, and the other one is A star, B N, C N, right? So this language is a union of two context-free languages, so it's context-free. But the problem is that if you look on the string A and B and C n, there's going to be two ways to generate it, right? Either you generate it with A and B n counting, and then Cn is the C star, or you generate it as well, maybe I should write it back as I wrote it before, right? Either it's A and B and C star, right? And this definitely generate A and B and Cn, A and B and Cn. Alternatively, we take the union with A star, B and Cn, right? And this also generates this A and B and Cn. So you either generate it with the first part or the second part, and you cannot decide which one it is. And it turns out that one can prove for these specific grammars that every grammar for it must be ambiguous. Inherently, because A and B and Cn is not a context-free language, right? So if you could somehow make it non-ambiguous, this would imply that this language must be context-free language, but we know that it isn't. That's the intuition of what's going on. And in fact, the problem is really difficult. If I give you a grammar, deciding whether or not it's ambiguous is undecidable. It's essentially equivalent to deciding whether a program stops on a specific input, which is stuff we're going to talk about later on. So it's really, really a difficult problem. Essentially, it cannot be done by a program. Okay, that's it for now.